There are a couple of different ways to build heaps. Let's begin by looking at building a heap from scratch. Okay, you may ask, why would we want to do this? When we actually get to looking at sorting algorithms and we look at heap sort, you'll see that the data is initially in a heap, and then it is sorted from that state. So we may simply want to take the elements and place them into a heap form. So the simplest way to do this is obviously to begin with an empty heap and add everything from scratch. And this was proposed by John Williams. It's attributed to him. And the idea here is that we'll continue to extend the heap as we add new members. So we have a sequence of operations that we want to perform on an empty heap. So let's begin by enqueuing. So you'll recall that whenever we enqueue to the end of the heap, and then we heap that element up. So our heap is currently empty. Let's enqueue 10. Okay, so the 10 goes at the end of the heap while the heap is empty, so the 10 goes here. And if we interpret this array as a binary tree or as a binary heap, it looks like this. 10 has no parent, so there is nowhere to heap up. And so we're done with this instance. Let's now add 8. So we add 8 to the end of the heap, and we attempt to heap up the 8. So let's draw it first. And so if the 8 is greater than or it's equal to its parent, it should be swapped with its parent. This is not the case here. So we have both a complete binary tree. So we have our structure property and we have our heap order property, because at every location, any node that has a child, that node's value is greater than or equal to that child's value. We then enqueue 20 at the end of the heap. Let's interpret this as graphically. And now we have to heap up the 20. Well, in this case, we see that we do in fact have to move the 20. 20 is greater than or it's equal to its parent 10, and therefore we're going to swap 20 and 10. This is we're going to just swap these two. This is not a rotation. This is just swapping these two values. Okay, and so in the array, it's going to look like this. We're basically going to put the 10 here and the 20 here. And we'll redraw the tree to just keep everything clean. The 20 is here, excuse me. And then the 10 is here. And then the 8 is here. So we began by heaping this node up. We will continue to try to heap the 20 up until it's either the root or it no longer violates the heap order property. In this case, the 20 is now the root, so we can stop the heaping. Let's look and see if we have our heap order property. 20 is greater than both 8 and 10, and 8 and 10 have no children, so we have a complete binary tree. It's actually full as well, and we have our heap order property restored. Let's enqueue 6 at the end. And so that looks like this, and extending our tree. Okay, that looks like this. And so whenever we enqueue, we try to heap up. And so we ask the question, is 6 greater than or equal to 8? It is not. And so the heap, so we don't heap anything up, and our data now looks like this. Let's add the value 13 to the end of the heap. And adding 13 to our tree is the equivalent of placing it here. And now we have to heap up 13. Well, 13 is greater than or it's equal to 8. It is. And so we need to swap these two. Okay, once again, this is not a rotation, and that yields this particular binary heap. Okay, and the 8 is here now. And notice we still have to keep trying to heap 13 until 13 is at the root or it no longer violates the heap order property. In this case, it no longer violates the heap order property, so we exit the heaping let's check for our heap order property here. So 20 is greater than or equal to both 13 and 10. 13 is greater than or equal to both 6 and 8. When we swap these, we actually swap the 8 and the 13. So the 13 is now here and the 8 is here. Okay, and then the rest of these nodes have no children, so they're fine. So we're back where we should be having our structure property. Okay, it is a complete binary tree, and we have our heap order property, which we just checked. Let's enqueue 17, and that goes in this position, and graphically that looks like this. Okay, and we have to heap up 17. So whenever we add something, again, we try to heap it up. 17 is in fact greater than or equal to 10. So we swap these two nodes. And then our tree now looks like, let's make that swap in the array itself. Okay, so the 17 is going to be here and the 10 is going to be here. And let's look at what that looks like. The 20 is first, right? That's element 0. And then the 13 is next. Okay, and then the 17 is next. And then the 6. Okay, and then the 8. And finally, it is now the 10 here. Okay, so this is our 17. And we're continuing to heap this node up until it's either at the root or it no longer violates the heap order property. It does not violate. It is not greater than or equal to 20 at this point. So we're able to terminate. And we are now going to dequeue an item. So you remember that to dequeue an item, we remove the root from the tree. We replace that value with the last element in the heap. And we then heap, we remove that element so we don't have two copies of it. And then we heap down from the root. Okay, so let's take a look at so when we dequeue, we're removing the root. Right, so dequeuing, we're going to remove this guy, right? So here's step 1, remove the root. That's step 1. Okay, here is step 2. Take the 10 and move it to the root. Okay, so the 10 is now here. Okay, and so that was step 2. I'm going to put these things outside of circles so that we know what they are. And finally, we're going to delete the 10 because we don't want two 10s in this tree. And let's redraw this tree to just make it cleaner. It now looks like this. We've got a 10 at the top, and we've got 13 and 17. We have the 6 and the 8. Okay. So when we made when we got rid of the 20, so let's work on our array now. When we got rid of the 20, we removed it. We brought this 10 into its place. and then we remove the 10. And this, what's in here, should be what's depicted in this tree. There's the 10, there's the 13, there's the 17, the 6, and the 8. Okay, we are now halfway through dequeuing. We must now heap the value 10 down. In this case, both 13 and 17 are greater than or equal to 10. So we're going to pick the largest, which is 17, and we're going to swap it with 10. Okay, and that, again, right, this is not a rotation because we're not, you know, we're really just moving these two things around, right here and right here. This now becomes the 17, and this becomes the 10. Okay, and now our tree looks like this. 17, the 13, the 10 is here, and the 6 and the 8. Okay, and we're still trying to heap down the 10. It started at the root. Well, the heap down stops either when we stop violating the heap order property, or when we reach the status of a leaf, which 10 is a leaf in this case. And so we can see that our array here, 17, 13, 10, 6, and 8, is this tree, 17, 13, 10, 6, and 8. Okay, let's dequeue. So that was the dequeuing. That was the dequeuing of 20. So now let us enqueue the value 5. Okay, so we add 5 to the array at the end. And pictorially, it shows up here. And we attempt to heap the 5 up. Okay, because whenever we enqueue, we will heap up. Well, there is no heaping up to be done since 5 is not greater than or equal to 10. And so so the enqueuing and the heap up actually terminates. And we've got 17, 13, 10, 6, 8, 5, 17, 13, 10, 6, 8, 5 in the tree. And that was enqueuing the 5. Let us now dequeue. You notice that again, dequeue does not take an argument. We're just taking the top item. So dequeuing, we're going to be getting rid of 17. Okay, it is a multi-step process. First of all, let's write that down, and then we will follow it. We will follow it through. Let's see if we can get a different color pen here. Okay, so let's look at the steps for dequeuing. Dequeue. Remove the root. Right, that's step 1. Okay. Step 2 is bring last node to root. Okay. Step 3 is delete last node. And step 4 is to heap down from the root. Okay, so let's do this to our tree. We get rid of the 17. Okay, that's step 1. Okay, we copy the 5 into the 17's position. That is step 2. Okay, we delete, so the 5 is now here. Okay, we delete the 5 that was at the end. right? That is step 3. And now we're going to heap down step 4. Let's give ourselves some room to do that. We're going to redraw the tree, having made some of those changes, and then we'll heap down. So here's 5. It's now the root. Here's 13, and here's 10. Here's the 6. And here is the 8. Okay, so what happened in our array? Well, we got rid of the 17. We moved the 5 in its place. Right, we've got the 5 from the end. We removed the 5, and this is where we are. 5, 13, 10, 6, and 8. 5, 13, 10, 6, and 8. We're now going to start heaping down, okay? So let's heap down the 5, and we're going to highlight the 5, showing that we're going to heap it down. We'll take a look at the 5's children and take the greater of the 2. If this was a mid-queue, we would take the lesser of the 2. Okay, so 13 is greater than or equal to 5, and 10 is greater than or equal to 5. So we will take the 13 and swap it with the 5, okay? And now in our array, that's all we're doing is we're just putting something in the temp and swapping it about. So now the 13 is here and the 5 is here. Okay, let's redraw the tree. So when we did that, the 13 ended up here. Okay, and then the 5 ended up here. Remember, we're heaping down the 5. That's what was at the root. So I'm going to highlight this, and let's redraw our tree. We've got 13, and to the left of 13 we have a 5. To the right of 13 we've got the 10, and then to the left of the 5 we have the 6, and then to its right we have the 8. And we're heaping down this node. To heap down, we ask if one of our children is greater than or equal to us for a max Q. Well, they both are, so we're going to take the higher child and swap. Okay, so then this swap takes place, the 5 and the 8. So let's do that in our array. The 5 and the 8. So the 8 then ends up here, and the 5 ends up here. Okay, so let's take a look at what that looks like. The 8 is now here, and the 5 is now here. And we're going to continue to try to heap down the 5. Okay, so let's redraw the tree, and we're just going to follow the algorithm through until it terminates. Okay, we're 6, and here's our 5. Okay, now we're here, and we heap down until we're either at a leaf or we no longer violate the heap order property. In this case, the 5 is at a leaf. This is the node that we started heaping down way at the top. It started up here, and we've gotten it all the way now to the leaf. And so now our tree, our array is 13, 8, 10, 6, 5. Our tree is 13, 8, 10, 6, 5. We have a complete binary tree. We have restored the heap order property, and therefore we now once again have a heap.